Yes.
Oh, you can. Okay. Great. Yeah, I was gonna look, so maybe someone knows this. Is Marlos's schedule full? I think there was like
Yes.
one slot left right after one, but no, that got filled up.
Yeah.
Then I don't have to advertise to fill your schedule. Okay. So I'm really excited to be able to introduce Marlos Machado. He was, of course, a PhD student here some years ago, working with me and many others. He has done a lot of work on discovering options, which I think would be of interest to a lot of our audience, and as well on exploration, which is continued. Some really cool work deconstructing everybody else's work on exploration and asking whether they're really doing anything, which is a great paper to go read if you're interested in exploration. But he's going to talk about something completely different today, which I'm really excited to hear about. So take it away, Marlos.
Thanks, Mike. Let me see if I can share my screen now. Can people see my slides?
That's good.
Yes.
Good. Okay, so yeah, let me start. So maybe even before I start, just let me say that I'm really happy to be back. I had big plans of going back to Edmonton physically, but obviously it's not possible at this point. Hopefully we'll figure this out soon. But yeah, so this work is a little bit different from a lot of the things that I've done in the past. And it was something that I started doing after I left U of A, and I'm really excited about the results. I think it's a really cool perspective on policy gradients, and that's why I wanted to present to everyone, both to get your feedback, but also because I think that this is pretty much opening up some new research avenues. So in a sense, it's also an advertisement. we're going to present this work again at NeurIPS in a week or two. That it was accepted, but here I have more time to present the work. Just to get this out of the way, please, if you have any questions, don't hesitate to ask me during the talk. I have 25 slides, so I definitely didn't plan that I'm going to talk very fast about everything. So if something is not clear, please let me know, and we can and I'll do my best to answer your questions. Okay, and this talk is a collaboration with Debo Gouche, who was a resident at Brang at the time that we wrote this paper. He's now a PhD student at Berkeley, and also Nicolas Leroux, who is a research scientist at Brang. And just to start, and in a sense, just give you a summary slide of the take-home message in case you get bored and you want to leave. What I'm going to show you today, the main message, is that we can see policy gradient methods as the application of two different operators, of an improvement operator and a projection operator. And seeing this policy gradient methods in this way, from this operator's perspective, it allows us to better understand connections to both value-based methods and policy gradient methods, and also to design algorithms or see algorithms in a different from a different perspective. And this is the general idea, and then of course I'm going to go over this, and I'm going to parse all these terms for you as we go. But if you're familiar to some of this terminology, this is the main gist of this talk. Okay, so let me start with some background, just to make sure that we are all on the same page. We like to organize things in science, right? Like, we like to say that there are methods that are from this class of methods and methods that are from this other class, because this does bring some clarity and allows us to import a lot of the intuitions that we have, and we show connections between these things. But in reinforcement learning, we often have these dichotomies, right? Like, we have model-free methods and model-based methods, and they are fairly different from one another. We have TD learning, and we have Monte Carlo methods, and then they are, in a sense, very different. And of course, we have eligibility traces that bridge this gap. And in a sense, one of the things that another class of methods that we have in reinforcement learning are what I call value-based methods, and then we have policy-based methods. Value-based methods are on this left side. It's like Q-learning. Everyone probably heard about it. Fitted Q iteration. If you want to think about the recent ones that are more famous, DQN, Rainbow, and things like that, which are methods that they try to estimate the value of each state in the environment. And as a side note, I took the liberty at RLAI to skip the agent environment interface and reinforcement learning, but we are still in the same setup. I'm just going to assume that people are familiar with that. If you're not, let me know, and I can try to clarify things as we go. But I'm still in the standard online setting where we want an agent to maximize the expected return. And what these value-based methods do is that they, given a state, they try to estimate how good that state is, right? Or given a state and an action that I would take in that state, how good that is, meaning how much return do we expect to accumulate through that? And then once we are going to have larger state spaces and we want to parameterize this because we cannot fill everything in a table, in a lookup table, we parameterize these value functions. So we have a function that is learning to estimate the value of a state. The alternative that we have are policy-based methods, which instead of trying to directly estimate the value of each state and then taking the action that's going to take you to the next state that has a higher return, that has higher value, we directly parameterize the policy. And we say that, okay, instead of trying to directly estimate the value, instead of estimating the value of a state, what I'm going to do is to try to directly estimate the policy itself. And I'm going to parameterize a policy. And as I see something better, I'm going to directly change the policy that I have. And we also have a whole slew of algorithms that are fairly famous nowadays. We have reinforced in the past, but now we have PPO, TRPO, MPO. And of course, there are things that bridge this gap, like actor critic, but overall, I would claim that it's a pretty disjoint set of algorithms. I would claim that it's not uncommon that someone spends a big chunk of their research career in only one side of this, and they are not comfortable implementing or developing algorithms for the other side. And when I was at Brain, I was always talking with Nicolas about this, and I was definitely more comfortable on the value-based side, but he's an optimization person. He was definitely more comfortable on the policy-based methods. And we wanted to connect these things, and this work is, in a sense, the outcome of this. So what I mean, just to be a little bit more precise, what I mean about value-based methods and their operators is that when we're talking about estimating the value of a state, and by value here it's V, we can see a lot of the algorithms that we have as just applying an operator on the estimate of this value function. In this case, the operator is this operation here, that it's the max over the return, the reward plus the discounted expected value of the future state. And what we know is that basically we can write our algorithms this way, right? Like Q-learning, we can write Q-learning about this way. And even though oftentimes we just write the update rule, when we are doing some more theoretical analysis, or we want to write these things in matrix form, we often write them in terms of operators, but in a sense, it's very similar to what we are used to. Obviously, this operator that I'm writing here, it's in the tabular case because I'm assuming that I can list, I can look up the value of each individual state in the environment, right? But if we have to go to the larger settings where we actually parameterize this value function, there is a second operator that we apply, which is a projection operator, which basically what it's doing is that I'm going to apply this operator that is going to generate a better estimate of my value function. But then I cannot represent all possible values of my state because I'm not tabular anymore. So I have I'm limited by the space, the function space, the function class that I define my value function to be. So, which is vpi, because now we are going to be parameterizing this value function with a set of parameters theta here, sorry, not vpi, the theta. And what we do here is that, so the way we generally do this when we're doing function approximations, that we generate a better estimate of the policy, but then we have to think about a projection because we have to make sure that we can represent the value function that we have. to exemplify this, I just copied and pasted a picture from Rich's book that I really like, which shows different forms of projection that we can have. But I think that overall, this captures what I'm telling you about, which is this notion that we have a value and then we do an improvement. Let's say we compute a new value, but then we have to project back, and then there are all sorts of different ways that different projections that we can have. The Bellman squared error, the value error, and so on. I'm not going to discuss this, but it's just to say that this is a fairly established thing in the field, and this is how we generally think about value-based methods in a way. The reason it's good is that the proofs are like, once you start to become more familiar with this machinery, the proofs become more straightforward. Like you can just invoke Banach's fixed point theorem, and then you can start asking questions like, does this operator have a fixed point? Is the operator a contraction? And then you start to be able to provide theoretical guarantees about a lot of these methods. Personally, I find them quite intuitive because they help with some of my mental models. We think about the value of a state. So we literally know how good the state is, what do I expect to get as a return from that state onwards. We can think about the policy because the policy is going to be defined by those states. And the operators are non-local. So every time that we improve our estimate of the value, we are improving throughout the whole state space. So we know how, in a sense, everything changed. But the problem is that a lot of these analyses, they're not that well suited for some other settings, like function approximation, for example. I was telling you about the projection, but as far as I know, the vast majority, if not all, of the results that we have with operators, they are assuming, for example, linear function approximation, because it's really hard to discuss this beyond this setting. So they have some strengths and weaknesses, and you can see where I'm going with that, because then we go to policy gradient methods, which are, in a sense, they look like a completely different beast. Like even the notation is different. But what we are doing here is basically just trying to maximize the return as we were before, right? And I'm going to use oftentimes the trajectory formulation, which at least when I was at U of A, it was not that common, but it just makes things more succinct. So I'm just going to spend the time to go over this with you. What I'm writing here is just the definition of the return, where tau is a trajectory. A trajectory consists of states and action pairs, right? So it's the state at time step 0, the action at time step 0, and so on. This is a trajectory. I'm going to define the return of a trajectory as just the discounted sum of rewards that I observed in that trajectory tau. And the pi of theta tau here, what it's saying is that it's the probability that I'm going to observe the trajectory tau when following the policy pi, which is parameterized by theta. So if you think about this, what I'm plotting here is just that the probability of a trajectory times the return of that trajectory, and I'm integrating over all trajectories, which means that this is just expected return, right? Like we write this as j of pi theta, but it's just expected return. But notice that here, because we are parameterizing the policy with the parameters theta that we have, and you can think about this as, I don't know, a neural network or something like that, we can just do gradient ascent, and we can literally say, oh, I'm going to compute the gradient of this object, and I'm going to change my parameter so I can get a bigger return. And we just do this, and that's policy gradient. And the reason this is interesting is like we can import a lot of the results from stochastic optimization when talking about policy gradient. We can start thinking about this as just minimizing a function in a sense. So we can start saying that, oh, does this function have a local minima? What is the curvature of my space? What is the noise of my gradient updates? And we can import a lot of the results that we have from the literature with policy gradient. And again, as you can see, like the notation is different, the way we talk about these methods is different. So they look very different from value-based methods, if you will. And of course, one of the main gist of this talk is to just say that there is not one that dominates the other. That's why there are so many algorithms out there from the different fields, and each one has its strengths and weaknesses. One of the strengths of policy gradient methods is about the convergence guarantees. Like it's much easier to prove results because in a sense we can just import some of the assumptions that we have from Robbins and Morrow and things like that, and we know that like if you define things properly, if you have low noise in the gradient, you're going to converge to a stationary point, at least a local minimum. I don't think that the mental models, though, at least for me, they're that easy because we are directly changing the parameters. So the reason is not that straightforward for me on how this impacts the policy. It's hard to think about policy space, and updates are very local, right?
Like, can I ask a question?
Yes. Yep.
You mentioned that the convergence guarantees are easier, but it always struck me that they were just weaker, that they don't mean as much. Like, I mean, if I want to just converge to a stationary point, I could just set alpha to 0 and get convergence. Like, it's not like, it's not like convergence to a stationary point is really all that exciting. So I'm wondering if you can comment on that. Do you think that how do you think about this? We can get easier guarantees, but are they as meaningful as what we might be able to say about minimizing, say, projected Bellman error or something like that?
I mean, clearly, if you set alpha to 0, no, right? I think that I tend to agree with you that they might be weaker, but I think that the difference is also because of the generality of the results, right? Because this applies to neural networks, for example. Definitely, I'm not thinking about setting the step size to 0 and then being to a stationary point, but it's just like we know that.
I guess characterize my caricature. It was just saying, like, if that's something you cared about, if like you worried, oh no, I don't know if this is going to converge to a stationary point. Oh great, I have theory. I mean, if you just decayed your step size fast enough, you could always achieve that. Like, you don't even need, by fast enough, I mean, just set it to 0 at some point, and then.
Sure. Yeah. But I think that
it feels meaningless as a criteria, as a result.
Yeah, but I think that this is it's almost an apples and oranges comparison. Like, because if we want to restrict our results in the same function class, let's say just linear, right? We can say much stronger things about policy gradient methods, right? So like this vague statement that I made, it's just because in a sense we can make vague statements about different function classes. But if you go to linear function approximation, then we have much stronger guarantees as well. I think that's the one of my main intuitions about this. I mean, in a sense, I mean, the last bullet here, it's also it's in a sense agreeing with something that you said, Mike, because it's also limited, right? Like, because we are importing results on, let's say, supervised learning or stochastic optimization, it's not that we can just apply this everywhere. And once we have the things that we do in reinforcement learning, like actor critic of policy learning, then a lot of this machinery doesn't work. So there are pros and cons on both ends, I would say. And the goal, of course, was or what I'm going to show is that I'm going to try to bridge this gap and show how we can import some of the mental models that we have from value-based methods into the policy gradient methods and see what this buys us. Okay. I don't know if there are any other questions. Maybe this is a good time to ask them. No? Okay. And I'm not seeing the chat, by the way, so if someone raises their hand or something, you have to let me know. So let me start telling you about reinforce, which is now I'm going to go to explain to you what is the gist of this operator's perspective that I'm talking about. Reinforce is one of the first policy gradient algorithms that came up. If anything, I think it's the simplest. And the idea is literally that you're going to compute the gradient over the expected return, which I wrote before. And if you do some manipulation, this is what you end up getting. And what this is showing you, this is the gradient of the return, is that the gradient is just the probability of the trajectory times the return of that trajectory, and then just the gradient of the log of the policy, and this policy here is parameterized by theta. Okay, so this is reinforce. The reason reinforce is in a sense cool is that we can think about this. We can just do stochastic approximations of this gradient, because this is the probability of a trajectory. So basically now we can just do samples. Take samples from this trajectory, which means by just executing the policy, we are going to naturally get the return of each trajectory, and then we just compute the gradient. And then basically what we're going to do here is we're going to take the log of the policy, and we're going to just scale that by the return of the trajectory. And that's reinforce. The main insight that we had is that instead of thinking about reinforce as from this perspective, like, okay, there's an expectation here, so we can just take samples and it's going to be an unbiased estimate of the gradient and we are happy. What if we saw these terms, instead of thinking about the stochastic estimates, as we reinterpreted this term as a new real-weighted probability distribution. And what this is saying here is the following. The probability, what I'm going to do here is that we know, let's imagine that, so this is a probability distribution across all trajectories. And what reinforce, one way that you can see reinforce is that is changing this distribution by upweighting the trajectories that have higher return and downweighting the trajectories that have lower return. For this to hold, we have to assume that the returns are greater than 0. And I'm going to relax this later on. But we can see this first part of the reinforce as a new reweighted probability distribution. If you do that, now you're going to have a new policy, pi prime, which is just what I described before, which is pi tau times the return. And if you look at this, which is just the same equation that we had before, this is literally the KL divergence between the previous policy that we had and the current policy that we had. So basically, this and this is it's almost underwhelming given in a sense how few steps there is here. But the intuition here is that instead of seeing reinforces just computing the gradient and then doing this, taking the samples from the gradient, we can see reinforces first generate a new probability distribution, which is pi prime, and then project it back to the space of realizable policies with the KL divergence. I'm not going to parse this theorem for you. I'm just putting it here to mention that there are some normalization constants on the value function at the bottom, the expected return, that ends up increasing the probability of good trajectories as well. But this is it. This is the main idea that we had, like the main insight. And just to put everything together then, what we are talking about is that we can see reinforce as the successive application of two operations. First, an improvement step that is going to generate a better distribution, if you will, by upweighting the previous policy with the trajectories that have a higher return. And we are going to, after we have this new distribution, we're going to project it back to the space of realizable policies using the KL divergence. And if you do one gradient step of the KL, every time that you do an improvement, you recover reinforce. And that's it. Are there any questions about this?
Yeah, so there was another paper bridging the gap between value-based and policy-based methods. I think Nashum and Mohammed Norzi and Dale, something like that. It was very, like, it looks very similar in that, like, they were also interpreting policy gradient updates as KL divergence. So I wonder if you've seen that and how that compares to this.
Yeah, I mean, thinking about policy gradient methods with the KL divergence is definitely not new. Like, there are control as inference, and there are all sorts of other methods that do that. I think that, yeah, so I'm not going to, I mean, I don't recall the details of Mohammed's and Dale's paper to go into the details, but I think that the main site is not about the KL, but it's about this notion of operators, the way that we're doing it. Yeah.
Okay.
I have a question.
Yeah.
So the policy here, when it's defined on the whole trajectory, right? So when you're changing these probabilities, I have a hard time imagining how you change the policy parameters, how that impacts the distribution over the whole trajectory. Because now you're not just saying I'm changing the probability of the actions, you want to change like where you get to.
Yeah, we are looking at the whole trajectory.
So how do I optimize this projection step then, I guess?
Yeah, so this is definitely theoretical, and at this point it is not. I mean, yeah, the trajectory formulation is not the one that we are going to use to optimize that, but it's a good leeway for this next slide, which is that everything that I told you in the trajectory formulation also holds for the state action formulation. And we have results for both in the paper. So when we are improving the and when the trajectory formulation, we are waiting by the returns and the trajectories. But when we go to the Q values, what we're going to do now is that we're going to have an estimate of the expected return with the Q, and we're going to just upweight the probability of the policy by the Q values. And I think that in this context, it becomes much more natural, at least for me. I don't know if it helps you. And the KL divergence also, instead of having a KL between all the trajectories, now we are going to have a conditional KL that, given a state, we are going to minimize the KL between the distribution of actions. Does this help you to build some intuition on this?
Yep. And are these two things equivalent? Like optimizing this conditional KL divergence is equivalent to the original form?
Yeah.
Cool. Thanks.
Yeah. I mean, there are all these standard tricks, right? Like we have to invoke the policy gradient theorem when we go to the state action formulation and those things, but at the end we get something like that would be the equivalent version of reinforced for state action pairs.
I have a question, Marlos. Can you go back to the previous slide?
Yep.
I'm just trying to, something doesn't sit right with me on the improvement step, and I think it's partially trying to think of like what space is pi prime in. So is it a policy? Is it an unnormalized policy?
Yeah, that's a great question. I think that I only understood that once I implemented it. So if let's just think about it in the tabular case to make it easier. The pi prime is a probability distribution across all state action pairs. So it's across the whole state. Like, of course, I'm talking now about state action formulation, but if you sum to 1 across all state action, so if you sum all the probability of all state action pairs, then you have 1. So that's the probability what the probability is over. Then, of course, in the trajectory formulation, it's across all trajectories, but that's too hard to think. So in the tabular case, you can think about state action pairs. Does it make sense?
That's interesting. So, okay, so now this is some sort of, there's implied in these is some sort of visit distribution, right? Like in order to have this sum to 1 over all states and all actions, then that means like there's something storing in the probability of just even reaching that state to begin with.
Yeah, I mean, this is a theoretical result, right? But
that's fine. I'm just trying to understand it. I'm not worried about practicality.
But definitely. So we have the stationary state visitation distribution d pi in all the gradients and so on because we are taking care of that. And eventually, when we go to the projection, then we are normalizing things back to, like, at least here in the state action formulation, we have a policy, and everything that I implemented has been on this state action formulation. For me, thinking about the trajectory formulation is just too hard.
Okay, I think that helps a little bit. Thanks.
Thank you. So if we have this, and I just want to reemphasize that from now on, I'm going to be talking about R times the policy, the return times the policy, or Q times the policy. And this is what I mean, which is this notion that I'm upweighting the policies. Once we have this this new thing,
sorry,
we can start as...
I'm sorry. On the previous slide, you're probably going to answer this for me later, but is S sampled from U?
Where are we?
Conditional KL divergence. Mu is the policy, but it's also S is sampled from U. I was going to ask you what that means.
So mu is the policy. Yeah. So basically, we are generating data from mu, right? And we're trying to find the new policy pi that is realizable that comes from. Sorry. Yes. So basically, we are using data from mu here because this is the policy that we had. We improve it. I think that there is a notation overload here. That's the problem. And then we are going to learn the new pi.
Got it. So mu, it just means that the actions to generate the state trajectory are obtained. The states generated for this expectation are the ones that mu would generate if you ran it in the MVP.
Yes.
Okay, thanks.
Exactly. So we can then ask some questions about this, right? Like, because if I just show you this slide and then it's like, yeah, that's cute, but so what? What can we do with this? And I'm going to answer 3 questions for you in this talk. One is that, well, I keep saying that it's an improved policy, but is R pi always a better policy than pi? Is this actually true? Can we write other policy gradient methods in terms of operators, or is it just a neat thing that reinforce lets us do? And of course, can we design better operators or better algorithms? And as you can imagine, the answer for these 3 questions is going to be yes. Otherwise, I wouldn't be giving this talk. So let me try to give you some answers on the second half of this talk. Is R pi always a better policy than pi? The answer is yes. And like we have a theorem in the paper, I have a proposition showing this. The reason I wanted to put this result here is because, as a lot of the things that I'm going to say in the second part of this talk is that, and the reason I like this perspective is that it helped me understand some policy gradient methods, and this result helped me understand a little bit a different facet of this method, the policy gradient methods. What I'm showing you here, what we are quantifying here, is exactly how much the improved policy is, how much better the improved policy is with respect to the previous policy. So the expected return of the improved policy compared to the expected return of the current policy, right? And this is the expression. And what you can see here is that this second term here is exactly how much better it is. This is the expected return squared. So this is, in a sense, it doesn't matter. But what I think it's interesting here is that when you look at the numerator here, a policy is going to improve more if you have a policy, if the policy that the previous policy has a higher variance over the returns. Which is interesting to me, because what this is saying, in a sense, is that, well, it confirms some of the things that I think are kind of known in the community, like deterministic policies for policy gradient can be really bad because you can be stuck in local minima. It ties to a topic that I've done a lot of research on, which is exploration, right? Which is just like, well, in a sense, this is justifying exploration for policy gradient methods because we do want to have diversity on the return because this allows us to improve things. And so in this context, I think that this is quite an interesting result, and it starts to justify things that other people do, like entropy regularization, for example. Why in the world would you do that? Well, clearly you're increasing the variance over your returns, and this might be a good thing. Like we can show that this is a bigger variance is going to have a bigger, it's going to lead to a bigger improvement, which means that you're going to have a bigger policy. So this is just one slide that I want to mention, but I think that it's good because it grounds this notion that yes, it's an improved policy, but it also starts to justify some of the things that people have done or are doing until today, right? Not only that, then we can start asking questions like, can we write other policy gradient terms in terms of policy gradient methods in terms of operators? And of course, the answer is yes. Yeah.
Can you go back a second?
Sure.
It feels a little bit funny to me, but I think it comes back to, again, I think the question I don't think I fully heard an answer to yet, which is what representation is this improved policy in? Because this seems to suggest that you can always improve the policy, right? That term 1 plus blah, blah, blah. I mean, yes, there's a pi in those values, but those values are still going to be like, that's still going to be a positive number. It means that even if I'm at the optimal policy, this seems to suggest I can make a policy better than that. That is not true.
Well, but then it depends on the return, right? Like if your return is it starts to get small, then this is not going to hold, I think.
But if I'm at the optimal policy, I don't understand where that.
Oh no, then the variance is 0, right? Then you're good. It's done.
Why is my variance 0? Can't I be at the optimal policy and there's still variance on my return, like, you know, stochasticity in the domain?
Oh yeah, but then it comes the second piece, which is like when you project back, like this is not a result that I'm showing here, but like when you still have to project your policy, right? And you're going to project to a fixed point, and then if you're at the optimal policy, when you project, you're always going to project back to the same fixed point. So you might improve, but then you cancel.
Okay, so that means this is space that we're talking about the improved policy in isn't really a policy.
Oh yeah, no, this is the first part. Let's put it this way.
Right, and so then I guess the question becomes, what is even the perform? Okay, so then I don't know what to make of IR pi. Like it's not really a policy in and of itself. And when you say, but the performance of it is this, how do I think? How should I even think of the performance of a policy like that isn't a policy?
Yeah, you should think about it in a way that if you have the right projection, it's correlated with improvement. And in a sense, has been a lot of the research that we are doing since we wrote this paper. But if you have if you have the right projection, their projection is not going to undo the progress that IPy is doing. And then you're improving. But if you have the wrong projection, then it becomes a mess.
So if I was just like in a single action setting where I only have like one choice, does that mean that like the way I should think about this is IPy or IR of pi is like a policy that puts even more probability than 1 on the best action? Like let's suppose I'm already taking the optimal action. Like IR pi is going to like move me outside of the policy space, and then projection pulls me back down to like what the optimal policy is?
Yes, if you're doing function approximation. If you're not, then there is a normalization term that I'm hiding everywhere to make sure that, but yeah.
Okay. All right, thanks.
So let me show PPO, because it's kind of an algorithm that everyone knows, and just to show what the improvement operator is here and the projection. You can see that I wrote it down here. It's not easy to get these operators from other algorithms. It took us a while to derive them. So it's not that there is a magic formula or a magic procedure to extract operators from every policy gradient method. But I think that once we do this, it starts to again shed some light on these algorithms. If we look at PPO, and if you recall what reinforced does, we see some differences. The first thing is that this is not being depicted here, but PPO doesn't have the same normalization factor that we have with reinforce. So it's not explicitly increasing the probability of good states, because as reinforce wasn't, as I showed the normalization in the theorem. Instead of, if you recall, so instead of using Q, it's using the exponential of Q here. And this is one way to address the problem of assuming that you have only positive returns, because now you can have negative values, and this is just going to be a very small value. And it's not multiplying by pi, which is interesting, because by not multiplying by pi, you can have arbitrarily small steps, because we're not directly changing the policy. And because it's exponentiating, if you try to prove results for fixed point, if you try to get fixed point results, what PPO does is actually use the reverse scale. And what I mean by that is that the KL is not symmetric. So if the element that you're minimizing is like if you're trying to find C and Z is in the second term here, we call it the forward KL. Otherwise, we call it the reverse KL. It behaves differently. But we know, like, this is the reverse scale. And just to give you an intuition, what this is trying to do is to match this, is to find this distribution Q that matches P. And the reverse KL is known as mode seeking, because it's really happy to latch on one of the modes of this distribution. And to avoid this, and in terms of policy gradient methods, you can think about P and Q here as actions. So it's really happy to come up with a deterministic action, or deterministic policy, the reverse scale, which I just showed you before that it might not be the best idea. So what they do is that they clip the reverse scale. So again, it starts to, like, we start to be able to see some of the justifications of what these methods do and understand how they do it. There's another algorithm, which is MPO. And MPO, now it doesn't have the problem that PPO has, that it's not multiplied by the policy. So in a sense, you're not going to have these arbitrarily small steps as you would before. And it's using the forward KL, which is interesting, because as much as I tried, I couldn't prove a fixed point result for MPO. So I don't know, maybe it's the wrong projection. It seems to work well in practice, but it's also an interesting observation. And just to be complete here, this is the forward KL. So in this case, the forward KL will try to match the distribution instead of latching on the mode. Okay. So just to summarize what I presented so far, like, we can start building a table, right? Like, we can think about, oh, there is this. The new policy is Q pi, and the forward KL we have reinforce. This is MPO. This is PPO. This is the result that I didn't show, but if you use the exponential, the operator of MPO, but you use the reverse scale, you recover reinforce as well. And the colors mean I was able to prove fixed point results. Yellow means I was not able, I didn't try, and red I tried and I failed, and I think there is no fixed point here. And as you can see, there are like gray squares, because empty entries in this table, because like it's begging the question, are these algorithms valid? And we actually didn't try. Like, we're exploring some of these ideas, but this just starts to show you how, like, this makes it very obvious and opens up possibilities of how to explore policy gradient methods in this context. the final question is like, can we design better operators? And then going back to Mike's question about how do I think about this improvement, like we want to have improvement as aggressive as possible, given that the operator is correct. So given that the projection is correct. So one way that we can think about this is that, well, I want to, let's say that I'm listing here, I'm enumerating all possible trajectories in my environment. And I have the ones that give me very high return, maybe the optimal ones. So shouldn't I just put a lot of weight on those trajectories and just move my policy towards those optimal policies? One way we can do this is that we can add a polynomial transformation over the rewards. And let's say we square the rewards, the returns, if we want. So now we are going to put even more weight on the trajectories that are higher, that lead to higher return, right? This seems a very natural idea. Like, do we want more aggressive operators? Of course, the problem, as I was discussing this with Mike, is that the policy might not be realizable in the set of policies, and then we need to think about the projection. And then the projection can undo a lot of this work. And this plot is showing this. Hopefully your screen is not too small. But what we are showing here is that this is just a four-room domain, and it's using function approximation. And the blue curve is reinforced, which is just k equals 1 and the forward KL. And now the other curves are more aggressive improvements, but they use the forward KL, which is not the right projection. And what you can see here is that it takes its cost because it does converge to suboptimal policy. Like it's wrong. You need to have the right match between improvement and projection because otherwise it doesn't work. So yeah, I mean, at first, by just naively changing the improvement operator, it doesn't work. But the result that I think it's really cool is that we actually were able to come up with a general class of projection operators for this polynomial transformation over the reward, this improvement, and it's something that is called the alpha divergence. And I'm sorry, as I keep giving this talk, I realize that I have to change the slides because I keep changing notation. But here, instead of having k, now alpha is equals to 1 over k. So the improvements is still it's still k here, but now it's 1 over alpha, and then you have the alpha divergence. I'm not going to go into details what the alpha divergence is, but just to give you an intuition, the alpha divergence is, in a sense, an interpolation between. It offers as a generalization over the KL divergence, and if you set alpha to 0, you're going to have the reverse KL. If you set alpha to 1, you have the forward KL. And anything in between, like alpha in between, is an interpolation between these two KLs. So if you use this generalization over the projection and you apply the polynomial transformation, then you have a fixed point result. And this is what we show here in this very contrived example, where basically the blue curve is again reinforced, but all those improvements that I showed you before, now they are not. You don't have to undo them with the wrong projection, because the right projection just accelerates learning and allows us to say that, okay, so this seems we can have more aggressive steps once you have the right projection. With that, are there any questions?
I guess I have a question. This looks really cool. I need to go read this and understand what this alpha divergence is. But when I was looking at the K, I was thinking that it looked like it was related to like a temperature parameter. You know, you're caring more about, you're sort of magnifying the larger values like a temperature parameter would as well. Is there any relationship there?
I'm not sure I know exactly what you mean by the temperature parameter in the KL.
Yeah, so let's say that I was trying to match some policy, like you're doing like softmax or Boltzmann or something, and you can, or like that, if you've seen like the Mellowmax operator, those are all kind of related. You can set a temperature parameter that says that it encourages you to concentrate more of your probability on the higher valued things, because in this exponential, you have the exponential sort of puts more weight on higher valued actions and reduces the weight on the lower valued actions. And if you set the temperature in some way, it starts to make everything more uniform. And so here you are sort of taking the values and you're exponentiating them, like you're magnifying some of the values. I was just wondering if it's somehow related to the temperature.
It is. I mean, once we go to the exponential transformation of the rewards instead of the returns instead of the polynomial, for example, we do have a temperature parameter, which allows us to do exactly that, right? To define how aggressive we're going to be. We never thought about the KL this way, or at least I never did, because, like, in a sense, the KL for these algorithms, it's fixed. Let's put it this way, like, oh, you use the forward KL or the reverse KL. So yeah, so I think that the temperature has definitely a role to play in the improvement operator, but I don't know if it has something in projection. But maybe it's good because Martha keep asking me questions that lead me to my next slide. Let's think about the tabular case where we can just ignore the projection operator, right? So now what I'm writing here is exactly what I wrote before, just a different way, but it's basically like the policy that I have is proportional to the previous policy times the estimate of my value function of the policy, right? And this is before we had k, but now it's 1 over alpha, but bear with me here. So what if we have alpha equals 1, we have just reinforced, like the standard, let's say, softmax or some other parameterization that you would have, which is just like, okay, every time I'm the improved policy is going to be proportional to the previous policy times the return. I'm just putting more weight. But now, if you think about this and you set alpha to, if in the limit alpha goes to 0, now you're putting all the weight into the highest state action pair, which is the argmax, which is super cool because if you stop to think about this, what we're saying is that for the operator view offers us an interpolation between reinforce and some value-based methods such as Q-learn. Because if you have alpha equals 1, you have reinforce. If you have alpha equals 0 in the limit, you have Q-learn. You're taking the argmax over Q. So by seeing these methods, and then it maybe it's a different way of answering your question, Martha. I don't know if this is exactly what you meant, but in a sense, how aggressive you are with respect to your estimates is how you can define, at least in the tabular case, when you're not thinking about these projections, this relationship between policy gradient methods and value-based methods. So if I want to be really ambitious, I can say that maybe one way of seeing this is that the same way that when we have lambda and lambda 0 in eligibility traces is TD, and lambda 1 is Monte Carlo Monte Carlo estimates. Here, maybe alpha equals 1, we have reinforce, which is just be the standard parameterization of the softmax, and alpha equals 0, we are going to have the argmax, which is what we have with value-based methods. Any questions? Good. Okay. So just to start wrapping up, this can also start informing us about other settings. It's not like a cute mathematical thing that we can prove these equivalences, but like, and now instead of 1 over alpha, I have k here in my slides. I should be less lazy, but what happens is that now, if we start putting all the weight in the trajectories of higher return, and let's say that we decide to be really aggressive and we set k to infinity or alpha to 0, and we're saying, I'm going to put all the probability on the highest returning trajectory. This starts to look a lot like imitation learning, right? Because we are putting all the probability on the best trajectories that we have. But what we learned with the projection is that if we are doing imitation learning, we probably want to use the reverse KL and not the forward KL, because that's the right projection to do if you want to focus so much on the high returning trajectories. And the reason this matters is because, well, we know some of the biggest successes in the field that we had so far, like when you think about AlphaGo, when you think about AlphaStar, they benefited a lot from expert data at the beginning, right, to accelerate learning. But I think that, I mean, I've experienced that, and I imagine others have as well. If you just try to initialize an agent with some policy that is better, the agent just unlearns. It's like it doesn't work. Like it doesn't work that well. And this is supported by some of the empirical data that I was presenting. But maybe what we can do then is to use the reverse KL, and this would be the right projection. And not only that, we can start thinking about more empirical approaches to do those things. And we can start thinking about, well, if I want to start from expert data, but eventually I want my reinforcement learning agent to kick in, maybe one thing that we can do is anneal the projection. In this case, it would be the alpha in the alpha divergence. And this is the plot that I'm showing here, like where the blue curve would be reinforced if you're just using the standard one. The orange curve would be the wrong projection, like if you're just being more aggressive, but you're not fixing it. But if you anneal, let's say this is the purple curve, you would then get the best of the two worlds, because you can benefit from more aggressive improvements or like some expert data at the beginning, but then you slowly decay so you can correct, which I think it's pretty exciting. Like it's a different area that we could explore about how to properly deal with imitation learning using this perspective. Just an overview again, we start to have more entries on this table, right? And like more empty entries as well. This table starts to become sparse. Maybe this is one of the reasons I want to give this talk is a call to arms if people are excited about this, because filling these boxes seems to be an excellent research project itself. But now we can have alpha divergences and exponential and polynomial transformations over the return. And then we have, in a sense, a whole class of methods here, depending on how we parameterize those things. But we can keep being creative, right? Like we can, well, if PPO doesn't multiply by the policy, can I just use Q? Or can I just drop the policy and things like that? And then again, we have more empty rows in this table. And I think that this, maybe the main message is that this framework, it gives us tools to think about these algorithms and to design new algorithms in a different way from what we had before, instead of trying to, I mean, at least for me, it always seemed very esoteric how you would come up with a new algorithm in policy gradient methods. So to wrap up, and I'm on time, the key takeaways of this talk, I would say, is that we can reinterpret policy gradient methods as repeatedly applying an improvement operator and a projection operator. And what I show you today is that how we can use this to better understand some of the policy gradient methods, understand the choices that they make, design some new algorithms, and also what I'm excited about, which is the notion of unifying different perspectives and algorithms in the field. The paper itself has a lot more that I didn't talk about, and we are doing some work on this as well after, since we submitted the paper. It's just like we have a lower bound on the overall improvement. So if you're familiar with CPI and TRPO and how they have an improvement, they have a lower bound on the improvement that they do. We have a different one that we are designing a new algorithm that we're quite excited about. We discussed what's the optimal off-policy sampling distribution. With this view, we can design that. There are other reward transformations that I didn't discuss, relationship to other methods, and like, for example, if you're familiar with control-wise inference and how we can see these methods as an EM algorithm and all those things. So yeah, so the paper is already available on arXiv. I think that it's already available on NeurIP's website as well, but it's available on arXiv if you want to check it out. And that's all. I'll take questions if there are any. Thank you very much.
Hey, Marlos, great talk. Can I ask, did you look at soft actor critic at all, at a comparison? Something which, I mean, they specifically optimize the policy such that by reducing the KL divergence between the policies distribution and the Q function there, how would that fit into this framework?
So just make sure, are you still seeing my slides or are you seeing me now?
I see you.
Oh, I'm sorry for that. We didn't specifically look at soft actor critic. All the derivations that we had, you had the entropy regularization term at the beginning, the operators and so on. And then I went back dropping off them because I thought that the math was too complicated. Like there are too many terms for the message of the paper. So it does support this notion of entropy regularization, but not specifically soft actor critic. It's something that we still need to do.
Okay, thanks.
Thank you. Any other questions?
Maybe I'll ask one more then if nobody else is gonna. So one of the things that I was thinking I could take away from this, and tell me if I'm wrong, is also that not any single policy gradient algorithm that we have necessarily is the right fit for all the different problems that we might look at. Is that kind of a takeaway from this as well? That maybe some policy gradient methods are better suited to different settings?
I don't know. Yeah, I don't know, because I think that maybe I'm thinking about imitation learning, and I'm thinking whether you want to have more aggressive steps in the reverse scale or something like that. And I think that I want to say no. I want to say that we were supposed to have an optimization algorithm to rule them all. We still haven't found it, but an algorithm that has the right, like a more aggressive improvement step and the proper projection. So yeah, I think that one of the takeaways is that it's easy to do the wrong thing. Like it's easy for you to come up with the wrong projection operator or something like that. And then maybe you have the right intuition, but then because you're looking from a different perspective, you can end up with an algorithm that is not good. Maybe it doesn't matter if you're designing algorithms in the old way, where basically you think about like a different bound that you want to optimize for, and then you try to decide the laws, and then you do it backwards, let's put it this way. But if you're trying to do this from the ground up, from this operator's perspective, I think it becomes very obvious as you go that, yeah, maybe I should try something else.
Okay, thanks.
Thank you. Are there any final questions?
I have a quick one, which is a follow-up to Mike's question. So there was this proposition that you showed where this improved policy is greater than equal to the performance of the old policy. And there's a term which multiplies 1 plus variance upon some squared term. So yeah, so there you mentioned that because we are just showing one of those things, like you are not projecting it back and we are talking about something intermediate. So if we're in the tabular setting, that intermediate policy is the improved policy, right? Like there's no projection going on. Projection will be back to IPy. So in that case, could you give some intuition about what's happening? So if I'm at pi star and the environment is stochastic, I do an improvement operation. I still end up at pi star. But because of the stochasticity in the environment, my variance term can be non-zero. So there should be like an equality condition here, right? But there seems to be strictly greater. So can you give some intuition about what's happening?
So yeah, I don't know if the let me just go back here. Maybe I shouldn't have stopped presenting, but hopefully you'll believe me. So it's greater than or equal to in the result. So definitely there is an equality there, and I think that the reason is just that, let's say that you're in the optimal policy, and then you have quote unquote still want to improve your policy, right? I swept under the rug a normalization term. So what would happen is that you're putting all the probability mass over already on the, let's say, the optimal policy, the optimal state action pairs, and then you have a variance, and you're going to increase that even more, but then you have the normalization term, and then it's just going to say, yes, you're already good. So it's just like, in that sense, the normalization makes sure that because the variance is like, it's still improving, but then the variance, like, it's the expected return, which is exactly what you have, right? Like that's at the bottom. So you just go back to where you were.
Okay, thank you so much for the talk, Marlos. That was really great. Just before we end, I just want to do an advertisement for Marlos that next week, pay attention. There's going to be a cool result that Marlos played a very important role in. So watch out for that and watch out for his name.
Thank you, Mike. It was a pleasure to be here.
Thanks, everyone.
Thank you, everyone.